For the final talk today, we have Altay Etkin from the University of Southampton, who will talk to us about Unimodular JT gravity. Thank you much.
Thank you very much for the organizers for inviting me here. We started actually this conference with 2D Young Mills, so it's kind of finishing with 2D gravity now, so I think it's a good wrap up. I will be discussing JT gravity in particular, but in this thing called unimodular gravity context. So this is the recent work that we did with Bruno, Alexander, and Farbot. He is sitting here, and Bruno is a PhD student at Imperial. Farbot is in Nottingham. He's doing his second year right now. So let me start. What is JT gravity? So JT gravity is a two-dimensional dilaton gravity model, which you model on a nearly anti-de Sitter or de Sitter two-dimensional space-time background. And the action looks like this, it's a very simple action. So you basically have phi as the dilaton, and little lambda is what we will call throughout this talk the cosmological constant. Why do we care about JT gravity? It basically captures near-horizon physics of near-extremal black holes coming from higher dimensions. For instance, you can do this in four-dimensional Reichenau-Nordsum. You'll end up with ADS2 cross S2, sort of near-horizon dynamics. You can also consider BTZ black holes, and in that case, it's just going to be ADS2 cross S1 in the same logic. So these are like effective actions that you get near the horizon of from higher dimensional theories. The ADS2 actually case is very interesting from the holographic standpoint of view. It's basically linking JT gravity with this thing called the SYK model, and because ADS2 has a boundary, there will be some sort of quantum mechanics living at the boundary of your ADS2 spacetime, and the theory that lives there is a 1 plus 0 dimensional, so there's only time basically, and it's called the Schwarzian. And it has been further shown very recently that by Saad, Schenker, and Stanford that this is actually JT gravity is described equivalently as a random matrix theory. So these are some motivations why JT gravity is kind of relevant these days in the literature. Like if you open archive, you see all of these. There is also interesting other limit of JT gravity, another two-dimensional dilaton gravity theory, and this is usually in the context of flat holography when you do 2 dimensions. It's basically just taking this little lambda to 0. So you might expect you just get phi r, and you might say, what do we do with that? But actually, Congeni and Jackiw in the 90s, they kind of wrote an action which is like 2. So they added this thing that we will call the vacuum cosmological constant. It's different from the little lambda. And this theory is very interesting because it's basically giving you some sort of description of flat space-time in 2 dimensions in terms of a holographic system. So for instance, what they do recently is that you want to actually study this Congeni-Jackiw gravity model at different temperatures when you take the path integral, for instance. And what you find is that the inverse temperature actually behaves like 1 over lambda, this vacuum cosmological constant. But lambda is a fixed number in this theory. So, and you want your partition function to depend on many values of beta, so you want the beta to run. And to do that, they basically consider this thing called the CGHS hat gravity model. And it's equivalent to the Congeni-Jackiw model on shell. And the modification is that you promote this vacuum cosmological constant to a off-shell variable, so you impose a Lagrange multiplier, and you add this U1 gauge field. So we will explore basically all these in the coming slides, and how actually these arises from BF type theories and the underlying structure group. As like I said, this 2D flat holography is basically connecting the CGHSAT model with the complex SYK, just like JT gravity is connected with the SYK. And the complex SYK has basically a extra U1 global symmetry in the theory. So, what am I going to talk about this in this talk? It's basically, we will see that actually the CGHSL gravity model is a two-dimensional Henneaux-Teitelboim mini-modular gravity theory. So that's the main message I need to give you. And for that, we will basically explain all these terms. So what is HT unimodular gravity? What is it new? And how useful is it in 2 dimensions? And we will also show that this actually arises for by taking the central extension of the isometry group of your theory that you started with. So if you start with JT, you will take the de Sitter group or the ADS group, and you basically do a central extension of that by U1. And you will find that all these theories appear from there. And we will see that all these theories are actually BF theories, and that they arise from the central extension. So they are HT gravity theories. Yeah, so I will do these basically. So let me start first by telling you about a little bit about what is unimodular gravity. So we first ask ourselves if we can, instead of having the full diffeomorphism, we can restrict ourselves to volume-preserving transformations. This is what Einstein asked himself in 1970. So that's just taking square root g equal to 1. You pick a very simple coordinate system. And turns out that the equations are not the Einstein's equation, but they're the trace-free equations. So I'm talking here about 4 dimensions, because this theory usually is in 4 dimensions. And I will then tell you why it's relevant afterwards in 2 dimensions, and how it arises. So the action looks like this. What Henneaux and Teitelboim did in 1989 is they tried to recast the diffeomorphism invariance instead of having volume-preserving transformations invariance. And this is achieved by introducing this T mu vector density. It's an auxiliary vector density that you introduce. And this term, basically, this 1, you just replace it with partial mu T mu. You can actually show that these equations are equivalent to Einstein's general relativity on shell, supplemented by the fact that this lambda, you make it an on-shell constant. However, it's an off-shell variable, and you impose this square root g equal partial mu T mu unimodular condition. So this will turn out to be very important. This allows us to introduce this thing called the unimodular time, which is just the spatial integral over some hypersurface, space-like hypersurface of my 0th component of my vector density. And it also tells you that you can see from here that lambda and T lambda are actually canonically conjugate pairs. So actually, by taking the second equation in 5 and do Stokes' theorem there, you will find that the volume of your space-time between 2 slices is actually a difference in unimodular time. And this number is a positive number, so it actually gives you a nice description of a flux for time, so it's a good observable, if you like, to describe a flow of time. Now, this HT term has basically not only diffeomorphism invariance, but it also has a gauge invariance. So if I do these shifts, imposing that I have partial mu epsilon with transverse condition, then actually the action is gauge invariant as well. This doesn't necessarily mean that unimodular time is gauge invariant, because you can have little large gauge transformations, so you have to be a bit careful on that. But the difference is gauge invariant. The HT term also has no local degrees of freedom, so this lambda and this T mu, they don't propagate. So you can ask yourself, okay, this looks like a topological theory. So what can we do? So this is what we did basically with Farbot and Joao like a year and a half ago, and we basically replaced this dt that you find here by f wedge f. And if you do that, you basically have some sort of Chern-Pontryagin term here. And then the t, you can find that is the Chern-Simons 3 form. So now you can actually integrate this, and you find that the unimodular time is actually the Chern-Simon number on a given space-like slice. And so, if you like, this paper basically explores the properties of what this might be on these sigmas, and it turns out that these are magnetic vortices. And so you have a change, topological evolution of these configurations on each hypersurface, giving you a flow of time, basically. It looks like this is what gives you a flow of time in this picture. So the question is, can we do something similar with JT gravity? Or does this happen in JT gravity? So I'll first give the first order formulation of JT. So this is based on taking JT gravity as a BF theory, and you take the isometry group of ADS2 or de Sitter 2 as your gauge group, and then you construct your SL2R algebra, which gives you the connection and curvatures, and then you basically define a BF-like action with these Lagrange multipliers, BA and phi. So this phi is my dilettante, TA is my torsion, and on shell you can see that by varying BA, you get torsion equals 0, and that gives you phi r tilde minus lambda sigma tilde. So these are your on-shell expressions that you will obtain by going just the equation of motion. And then if we go back to second order formalism, you find that it's JT. So this is standard stuff. And those two equations, they basically become this. And so you can either have a space-time which is anti-de Sitter, or you can have global de Sitter. This one is for closed universes in ADS2, so it's a bit more, it's a different story there, but it's still from a point of view of quantum cosmology, that's usually what they can consider in ADS2. This is more relevant for quantum cosmology and de Sitter spacetimes. So now, how does this HT thing arises? You basically introduce this vacuum cosmological constant that appeared in the Jackiw-Teitelboim model. So you can take a shifter. The first thing you can do is you need to take a shift of JT gravity dilettante by this vacuum cosmological constant. And this gives you this thing called the KSY model. No one uses this name, but these are the first guys who actually invented this. And it's basically an action which combines JT gravity and the Jackiw-Teitelboim model together. And if you look on shell, it's just a shifted JT. Like I can redefine my phi like that, because lambda is a constant, and this lambda is also a constant. So this entire expression is just JT gravity. But here is a bit more, I wrote it down like this explicitly because this is what we're going to take as a BF theory. How this arises as a BF formula. So the question is, how do we get the gauge-theoretic formulation of this model? Well, a naive guess or a proposal is that you take lambda, you make it a variable, now off-shell variable, and you introduce this auxiliary vector field. We will now see that actually this action 15 is this thing called, we call this HT2. It's actually a BF, it comes from a BF theory, but if you take the extended de Sitter algebra. So what is this extended de Sitter algebra? It's basically SL2R and then a U1. You basically do a direct sum. And then you introduce this central element I. And these are the commutators that you will get for the generator. So the PA and the J tilde, they are for the SL2R part. And from here, you will get some non-trivial components in your curvature, basically. So the SL2R hat, de Sitter, extended de Sitter algebra valued connections. You will add basically your U1 gauge field. And then the F turns out that if you compute dA plus A wedge A, you will get this extra term, F plus sigma tilde. Sigma tilde, by the way, it's the dual of the area form, area 2 form. So it's EA, EB, but I basically make the dual of that. And you obtain a BF type action by introducing this extra Lagrange multiplier, lambda, and you also add this torsion term again, and you go on shell here, and then you find that this is your BF type action that you end up with. And now you can ask yourself, okay, what is the second order version of this? It's precisely this one. So the question now is, does this have actually all the properties of an HT2 gravity action? So let me rewrite this like this. So I just take the epsilon mu nu A nu, and I write it down as this dual A nu notation, so it's like a densitized gauge field. And basically I can just say now that I can identify T mu with A nu, curly A nu. Again, this action is diffeomorphism invariant. There's a gauge invariance doing the same shifts of T mu. And there's also a topological term, clearly. So it has those properties. On shell, if you look at the equations of motion, so variation of phi and variation of the metric, you will find exactly the same equations as the KSY model, or this shifted JT gravity, but you also get these extra conditions. So from the variation of lambda, you get that root g is partial mu a mu, or partial mu t current c mu. And if you take the variation with respect to the gauge field, you will find that lambda, the vacuum cosmological constant, is of on-shell constant. So now, what else do we have? Well, we have the unimodular time, and you can just compute it. It's the zeroth component of t0, and these sigmas now are one-dimensional slices, and so you basically just get the integral of a. So if you can think of it, roughly speaking, as the one-dimensional Chern-Simons number. And again, that number cares about the topology of your underlying hypersurface, one-dimensional hypersurface. And of course, if I take this now, and I do again Stokes theorem, you end up with delta t lambda being the two volumes. So the difference of unimodular time is your space-time volume between two slices. So maybe some remarks. Unlike its four-dimensional cousin, so this U1 reduced HD gravity in 2 dimensions naturally emergent from this extended de Sitter algebra. We don't have this type of structure in this four-dimensional theory, and we just basically have replaced this f wedge f with f. And yeah, the Cauchy hypersurface sigma can, because we're in one dimension like the slices, it can either be R or S1. And S1 is more or less relevant for quantum cosmology. Yes, so from the on-shell expressions, we also have these two. So this is the lambda variation, big lambda variation, and this is the phi variation. You can see, you can actually relate F to R tilde. So this is a very interesting feature that happens. So in some sense, the gauge field A, the U1 gauge field A, is related to the spin connection. And this is up to an integer, because you have the large gauge, f equals 0 type of, no, I will show later that actually this n arises if you take a different a decoupled version of this theory. This n is basically giving you that you have pure gauge configurations. So you have winding basically. And again, flow of time is a difference of Chern-Simons numbers on each slices. Maybe I can skip this. How am I doing with it? So, yeah, this is a decoupled version. Basically, this is what you see more often in the JT gravity context. If you want to couple it with a U1 topological Maxwell term, so this is like a U1 Yang-Mills. And what you can do is you can take the extended de Sitter algebra and combine the J tilde and the central element I into another generator, L tilde, and then the algebra looks like decoupled. And so when you work out all the procedures again, you will just find that actually you will have your JT term, and then you have this lambda bar, f bar, sort of U1 topological Maxwell term with the varying, it's like a varying theta, if you like to think about it like that. And it is actually, this 24 is equivalent to HT2, because I can use this, and then I can rewrite these phi bars and lambda bar in terms of phi and lambda. And this A bar is actually A plus omega tilde. So for instance, here, if I go on shell, where I vary with lambda bar, I get f bar equals 0. So that tells me that locally I have pure gauge configurations. So that tells me that this A bar is like d theta. And that's why, for instance, here you get this n. Because if I integrate that d theta and I have large gauge transformation, I will get winding, I will pick up windings. And so that's why this is like telling you that A is related to omega tilde up to this integer n. But these theories are basically the same, like if you do this prescription 25. So you can view JT gravity plus U1 topological Maxwell as HT2, which is quite cool, I would say. At the start, I also talked about the flat limit, so the CGHSAT model. And actually, this is the lambda equals 0 limit of the extended de Sitter algebra. So if I just take lambda equals 0 in my HT2 extended de Sitter algebra, but not the decoupled theory, you will just get this very simple Maxwell algebra. And the BF theory is actually going to be the CGHSAT model. You can basically just find the A's and the associated curvatures. And then the BF theory is just basically going to be your CGHSF model. And the equations are basically just identical once more, not to JT or KSY, but to Jackiw gravity model. So we have these two equations as well, like the unimodular conditions as well. So everything is working out perfectly. You also have this gauge transformation, etc. Maybe another comment I can add is that you cannot write a decoupled version for this. Like I cannot do a procedure like I did here with the flat case, because you cannot do something like this. So this theory is like by itself unique. And we find the unimodular time like before. So it's the integral of A, and because of that, you cannot have actually this sort of identification. Because like the integral of A is the integral of A. You cannot relate it to the spin connection. So maybe a brief summary, I would say, is that we have this picture. So you have HT2 here sitting there, and you have all these limits. So if you take the flat limit, you get the CGHSF model. And if I take lambda equal vacuum cosmological constant to be so when I go on shell, I basically get the Jackiw. And if I take HT2 and I go on shell, I find that it's the KSY model. And its flat limit is the Jackiw. Or I can take actually just lambda equals 0, or just a shifted version of JT, and it gives me JT. So we have shown basically that a two-dimensional Henneaux-Teitelboim gravity formulation of Jackiw-Teitelboim and the Jackiw gravity is possible. And the most important thing is that this is actually from a BF theory. Like it comes from the underlying algebra and gauge symmetries and so on. Yeah, so this is basically the second part of the paper, but I don't have time to explain that. We basically applied this model to quantum cosmology, and we found some very nice results. We found that you get a unitary quantum cosmology model in the sense that your states, basically now that you have a time observable, your theory actually is unitary, in the sense that you can build the Wheeler-DeWitt equation transforms into a Schrödinger-like equation, and so you get nice evolutions. And we also found some topology changing aspects that if we consider basically if you take a de Sitter model and then you look for the expansion and contraction, how they interfere at early unimodular times. We can discuss that if you want later. And yeah, some outlooks. So what we are doing now, basically, we want to basically look for the connections between HT2 and holography, how it arises. And I told before that you have the CGHSF model viewed as a complex SYK. There are results on that. So we speculate that it's actually a sector. So the HT2 is a sector of the complex SYK, because it also has the perfect group for that. You have SL2R cross U1. This is the thing that appears in complex SYK. If you go low energy, the global symmetry of your boundary theory, this boundary quantum mechanics theory, has this feature. So it would be cool to relate HT2 to that formalism and then go to a random matrix model for that. I said here that you have some topology changing notions, Morse functions happening there as well. And so it would be cool as well to explore that more in detail. And finally, I might say, among many others, many other questions. I have 3,000 questions, but it's okay. One other motivation I can say to look into this is if this type of gauge-theoretic approach with the algebraic structure can actually be describing the F wedge F four-dimensional theory, for instance, and how it arises, let's say, in 3 as well. So, yeah, thank you.
Thank you very much. Any questions? Yep.
Qualitatively, how different is quantization of this model versus just saying quantizing JT?
So if you quantize JT gravity, you'll end up with, so first you do Euclidean, you go to Euclidean space, then you basically get a sum of the path integral will give you a sum over topologies over Riemann surfaces with arbitrary number of boundaries and genuses. Of course, that's for the orientable case. I would say that because you're adding, so if you consider the disk topology, the boundary description is the Schwarzian theory for JT. In this case, you basically modify that, so it's not just the Schwarzian. If you consider, for instance, this HT2 approach, or the complex SYK, you actually get the particle on the group U1. And so the quantization changes in that regard. So you don't just get the answer that you will get for this partition with the Schwarzian, but actually your theory will also incorporate this U1 degrees of freedom that you have at the boundary. In some sense, the density of states is going to change for your theory. In the random matrix theory model as well, the thing changes.
I don't need like cosmological signatures with this, like the difference between the two.
What do you mean by cosmological?
Well, you have like a 2D cosmology, right? Like you could
You meant that, yeah.
Oh yeah, just not like physical level.
Yeah,
if you
okay,
solve,
okay.
like, anything,
Yeah, I mean, the 2D cosmology approach is different because you get unitary evolution. So normally your quantum states are frozen because of Hamiltonian constraint. Let's say you work in a mini-superspace type of approximation, then basically that's a Wheeler-DeWitt equation if you quantize the field. And you will find that there are no time evolution. Like your wave functions are time independent. There's no time in the field because it's diffeomorphisms. Wheeler diffeomorphism there. And so what you're looking for here is how can you introduce some time, like in standard quantum mechanics, like in the Schrödinger mindset. And what you find is that this unimodular time actually does this. It precisely does its job. So it gives you a well-defined inner product, finite norms, normalizable states, Gaussian amplitudes, all of that.
Thanks for the great talks. Well, I probably spawned a common question. So if something like self-dual magnetosphere can also be written into kind of BF, do you think it to be any further crossover with that?
I would say instantonic type solutions might be relevant, I would say. Maybe in 4D as well in 2D. Actually, a paper by of Kangemi and Jackiw, as well as Kangemi and Dune around the 90s, early 90s, they actually found that this A looks like a 1+1 dimensional instanton type equation. So maybe that's, in that sense, there might be something going on. Maybe topologically as well. Like if I get the 2-sphere, that would be interesting to study how, like gravitational instanton type solutions, you can also obtain those, I think.
Thank you.
Just regarding one of the points you brought up at the end about generalizing this to high dimensions, where is the actual blockage? Where is it in terms of your algorithm of? So you start with like a gravity theory. You can presumably for any even dimensions build this unimodular framework, right? But is it the whole thing of writing stuff in terms of a BF theory that starts to break down, or why does it not already
I would say
exist?
first order formulation of general relativity is hard, right? Like that's the problem in 4 dimensions. In 3D, it's like Chern-Simons. In 2D, you can do JT with BF. In 4D, what do you do? There are 3,000 proposals on that. So it actually depends on what you really want to take as your structure group. You can take, for instance, the Lorentz group, and then you end up with Einstein-Cartan formalism. If you take the Poincaré group, then you end up with Poincaré gauge theory, and so on and so on. Like the ladder goes. You can also do Plebanski and all this stuff. The main point I would say is how do you combine this F wedge F in the gravity, like I did, in the sense that SL2R, if you essentially extend, you get the extended de Sitter, and this gives you HT2 directly. So the question is, can you have a similar group theoretic structure? It doesn't have to be essential extension, but any other mathematical tool, geometric tool that allows you to do that, yeah, that would be cool. We are actually also working in 3D, and yeah. So maybe another point I can add is that this HT2. So since it's a BF theory, you can think of a BF theory as a dimensionally reduced to Chern-Simons. So you might speculate that from a 3D perspective, this actually comes from a Chern-Simon action. And so you might wonder what is the gauge group for that, and yeah, and then connect it with physics. But 4D is harder. 4D you don't know what to do, I would say. So it would be interesting to see actually how you can do it in 4D. That would be a very cool result, I would say.
Thank you.
If I understood your time was going to be the Wilson line, basically, the integral of it. So it's going to be periodic, isn't it?
For S1, you mean?
Yeah.
Yeah.
So your time, so in your cosmologies, you have closed time-line cuts?
No. What you get is this. So you have let's say you have the de Sitter 2. You have this. And you slice your space-time. So this is your coordinate time. And when I slice, I basically get just these S1s at every equal time slice. I do.
But then your time was the integral on that S1 of your...
Yeah, so it's kind of going around the gauge field, but the time is flowing upwards, the unimodular time.
But wasn't your unimodular time the integral of A around that loop?
Yes.
So that's a Wilson line. So that's going to be, that takes periodic values. If you're in a U1 gauge.
So you're saying it's going around the circle, the time. It should go upwards.
I just mean the Wilson line takes values between 0 and 2 pi.
Yeah.
So
But I don't see how this is connected to T lambda enough.
we can
discuss it. Let's discuss it.
Okay, there are no more questions. Let's take that, I guess.